I'm a second-year PhD student at UIUC. In this talk, I'll be presenting our recent work, BlockFlex, enabling storage harvesting in modern cloud platforms. This work was done with Jinghan Sun and my advisor, Professor Jian Huang, as well as Anirudh Badam and Shadi Noghabi from Microsoft Research. Cloud storage is a core service in data centers today. Modern data centers are running storage-intensive workloads such as batch processing, graph analytics, or database workloads. As these workloads migrate to the cloud, they increasingly rely on cloud storage to fulfill their data needs. To implement cloud storage, providers maintain a large pool of storage devices. And due to their high performance and decreasing cost, these devices are increasingly SSDs. They are then virtualized and sliced among multiple application instances. Each VM sees a virtual block device, which the storage virtualization layer maps to the underlying virtualized SSD. Through storage virtualization, providers receive a number of benefits. Chief among them is the improved utilization through the ability to share resources. And also, you can hide the complexities of storage management from the upper-level users. For these reasons, storage virtualization has become the de facto standard implementation for cloud storage. Despite the many benefits of cloud storage and its widespread adoption, we see that cloud storage is still severely underutilized. Here's an example from Alibaba's cloud characterizing its storage bandwidth utilization for an 8-day period for over 4,000 servers. We see that at no point does the utilization exceed 31%, and on average, the utilization is only 8.6%, which raises the question, why is storage utilization so low? And to better understand this, we analyzed traces from cloud storage providers that characterize the bandwidth utilization and their capacity utilization. We find that the first source of low utilization is from unallocated storage. Here we have VM allocation and deallocation traces from Microsoft Azure spanning a 24-hour period for over 1,400 servers. We see that 70% of servers have unsold space. And we also see that 50% of servers have an average of 20% of space unsold. One major contributing factor is that the over-provisioning of resources for efficient VM allocations and for high availability. But unallocated storage is not the only reason for low utilization. We also see low utilization from allocated storage. Here we have traces from Google's cloud, which characterizes the storage capacity utilization for over 12,000 servers over a period of 29 days. We see that 20% of VMs do not use any of their allocated storage. And we see that 50% of VMs use only 26% of their allocated storage. Reasons for this include that users provision for bursts in their workloads, leading to low average utilization, and also limited capacity options when allocating VMs, forcing users to over-provision. One promising technique to improve the resource utilization is the harvest VM that has been used in data centers today. Here, the harvest VM is a low-priority VM that can grow or shrink to use the available resources in the server. For example, if VM1 exits, the harvest VM will grow to utilize the available resources. If we want to allocate a new VM, then the harvest VM will shrink to avoid eviction. What makes the harvest VM attractive is that it is offered with lower cost. Since it relies on available resources, it is offered at lower cost. And the fact that it relies on available resources means that it may be evicted at any point in time by the provider in order to make room for a regular VM, so it has lower guarantees. The harvest VM has successfully improved the utilization of CPU and DRAM resources. And this is because the existing virtualizations through vCPUs and virtual memories offer mature virtualization support for mapping resources among multiple VMs in a fine-grained manner. We also see that there's relatively low overhead for rescheduling these resources, so the harvest VM can quickly give up or take additional resources. This raises the question, what about harvesting storage? Could we harvest storage to improve the utilization? Unfortunately, storage harvesting is uniquely challenging. And as I've alluded to, the first challenge is the current insufficient virtualization support. The problem is, when we allocate a virtual SSD and we map it through the virtualization layer onto the underlying resources, we do not track what storage is being used or how it's being used. which means that with current virtualization, we have no clue which blocks would be harvestable. or how long they would be harvestable for. Even if we had virtualization support, there's still significant data security concerns we need to worry about. When VMs allocate their storage, applications assume full control of their allocated storage, and they rely on this when they store their sensitive data in the cloud. They do not want any other VMs looking at or accessing their storage. Even if we have secure virtualization support for harvesting, we need to avoid performance interference. Again, when VMs are allocated storage, they are guaranteed specific performance metrics, and the harvesting procedure may not interfere with these guarantees. Before we discuss how we can overcome the challenges of storage harvesting, let's first establish that storage harvesting could actually work. And the first question is there enough available storage that we could harvest? And the short answer is yes. When we analyze the unsold resources, we find that 40% of servers have the harvestable storage capacity that could be harvested for over 6 hours. We see that over 6% of these servers have even up to 50% of their storage available. So we've established that there is available capacity to harvest. However, these are still evictable VMs, so we need to be certain that the storage lasts long enough without being evicted for it to be useful. And again, the short answer is yes. Over 60% of the harvestable storage lasts over 12 hours, and harvesting of any size shows a low and stable chance of eviction. This leads us to the conclusion that storage harvesting is in fact promising. And to realize this promise, we developed BlockFlex, the first learning-based storage harvesting framework for modern cloud platforms. To overcome the insufficient virtualization support, we extend current storage virtualization with a ghost vSSD abstraction that makes managing harvestable resources easy and transparent to the upper-level VMs. To overcome the data security concerns, we enable fine-grained hardware isolation and block erasing to make sure the harvesting procedure does not leak data. Finally, we minimize the impact of harvesting on regular VMs by ensuring that we only harvest idle resources, and we prioritize the regular VMs over harvest VMs if there is co-location. Let's first discuss the virtualization support. In order to enable storage harvesting, we need to be able to track which blocks are harvestable and for how long. We also need to have the flexibility to manage the underlying blocks. Therefore, we would need to expose the low-level block information so that the virtualization layer can manage this. Luckily, software-defined flash already enables this. One such example is our previous work virtualizing software-defined flash called flash blocks, which mapped vSSDs to the internal flash channels of the SSD. By mapping vSSDs to hardware-isolated flash channels, we can achieve good security isolation and through hardware isolation and performance isolation as well. Flash blocks also address the challenge of wear leveling in software-defined flash. By periodically swapping which vSSDs map to which channels, we can ensure that the wear is balanced across the channels in software-defined flash. We build BlockFlex on top of this software-defined infrastructure, and however, this itself is not enough to enable storage harvesting. We also need to be able to easily manage the harvestable resources. And to do so, we enable a new abstraction for storage harvesting that we call a ghost vSSD, or GSSD. The GSSD represents free, harvestable resources from a vSSD. As mentioned, we have two potential sources of harvestable storage, from allocated and from unallocated VMs. So if a ghost vSSD is created from an unallocated VM, we could harvest the entire channel and put that into a ghost vSSD. If we harvest from a regular VM, we may take some blocks from all of their channels and turn that into a ghost vSSD. On top of this, we add three important pieces of information. The first is the bandwidth, which represents how many channels we have harvested for this GSSD. The capacity, which says how many free blocks we have harvested. And finally, the lifetime, which indicates how long is this harvestable storage available before it needs to be given back. After creation, the GSSDs are added into a GSSD pool. By using a pool, we can put the harvesting procedure into the background. The GSSD pool uses this metadata information in order to maintain a set of lists for each bandwidth and capacity pair. where each list is sorted by the lifetime. Then when a harvest VM submits a harvesting request, we can quickly return the best fit match to respond with the necessary resources. The GSSD abstraction is new, but it does not interrupt the existing storage virtualization. Instead, we added underneath current VSSDs by adding a layer of indirection. This makes the harvesting procedure transparent to the upper-level VMs, and it also allows us to harvest up to 256 GSSDs at once. Now that we've discussed how to manage the harvestable storage, the last missing piece is how to identify the harvestable storage. Remember that our harvestable storage resources could come from unsold or from underutilized regular VMs. And for different sources of harvestable storage, we use different approaches to identify it. Since unsold VMs have fairly predictable behavior and can be analyzed at a cluster-wide level, we use a heuristic-based predictor. We analyze the behavior of unsold VMs and then use that to create GSSDs and predict their harvestable lifetimes. However, regular VMs don't behave as nicely. They can have dynamic and unpredictable and unique workloads. Therefore, we learn their behavior in an online manner using a prediction workflow. To do so, we trace their I/O operations to infer statistics such as the IOPS, bandwidth, and storage capacity utilization. These are then fed as inputs to lightweight LSTM models that predict the necessary capacity and bandwidth for the workload. The capacity and bandwidth are then assigned lifetimes, and these values are combined into a single GSSD with the harvestable storage of the regular VM. For harvest VMs, we also need to be able to predict its workload requirements. Instead of generating GSSDs, we need to know how much we want to harvest from GSSDs optimally. Since these also need to be learned in an online fashion, we use a copy of the same prediction workflow and predict how many resources must be requested. By predicting which resources are idle, we only harvest the idle resources from regular VMs, and we only use the ones that are truly going to be used by harvest VMs to improve the efficiency of the harvesting procedure. Now, since we deal with predictions, we also need to be able to handle mispredictions. So we look at harvestable and demanded storage, and our predictions can either be over or under what the real value is, which can lead to three negative consequences. The first potential negative consequence is the waste of resources. But since without harvesting, all of these resources would be wasted, we don't do anything in particular to avoid this. For under-harvesting, this can happen when we underpredict how many resources a harvest VM needs. But since we facilitate harvesting up to 256 GSSDs, we can just submit another request to cover the difference if we mispredict. So we don't do anything else special here. Early reclamation is the most challenging because this can impact the performance of regular VMs. Analysis of our predictors on baseline show high accuracy of 86%. But in order to add a buffer in case we mispredict, we keep 5% of the harvestable storage with the regular VM in order to add a buffer for mispredictions. And we find that we avoid early reclamations in 93 to 96% of cases. Now that we've discussed how we extend the virtualization support, let's discuss how we alleviate the data security concerns and ensure performance isolation. The first thing we do to enforce data security in BlockFlex is that each GSSD is hardware isolated from the VSSD. So every block in the channel can only be accessed by the VSSD or the GSSD. And since it can only be accessed by one or the other, data cannot be leaked through shared blocks. Second, we only ever harvest free blocks that are erased, and after harvesting, we also erase all the blocks to ensure that no data is leaked through the harvesting procedure. And finally, in order to avoid VSSDs trying to access each other's blocks or mapping tables, we enforce permission checks within the storage virtualization. To ensure performance isolation in BlockFlex, we utilize the hardware isolation of the independent channels so that without harvesting, we have performance isolation. But inevitably, harvesting will mean that we share some resources. The fact that we only harvest idle resources helps avoid performance interference. And finally, we prioritize IOs from regular VMs on shared channels to ensure that even if there are co-location issues, they don't affect the regular VMs. We implement BlockFlex on a 1 terabyte programmable SSD, and evaluate it with YCSB for regular workloads and batch processing, graph analytics, and ML data preprocessing workloads to represent our harvest workloads. To demonstrate the improved cloud storage utilization, we add hypothetical harvest VM requests to all of the traces that we analyzed earlier. And we find that across all of the traces, BlockFlex improves the storage utilization by 1.3 times on average. Finally, to demonstrate the improved performance for harvest VMs with BlockFlex, we run a basic ML data preprocessing workload and then either harvest empty channels or channels that are also running YCSB. And we see that we can achieve up to 60% harvest VM improvement with BlockFlex. In summary, BlockFlex rethinks storage virtualization to enable storage harvesting, it ensures data security, and it minimizes the impact of harvesting on regular VMs. We also participated in the artifact evaluation, and our code can be found at this link. Thank you very much, and I'm happy to answer any questions.